Hey everyone, welcome back to the Programming Professor's channel, where we cover topics in software design. Today we're tackling a crucial topic, objects and data structures. We'll explore how these concepts shape the way we build flexible, maintainable code, and why understanding them is important for any developer. So let's jump right in and see what's on the agenda. Mastering Objects and Data Structures in Software Design. Based on Objects and Data Structures, from Clean Code by Robert C. Martin. Today's video is structured around 5 key areas that'll give us an understanding of objects and data structures. First, we'll cover encapsulation and data abstraction, why they matter, and how they protect our code. Then, we'll compare objects versus data structures, highlighting their unique strengths. Next, we'll dive into the Law of Demeter, a principle that keeps our code from getting too nosy. After that, we'll look at data transfer objects and their role in moving data around efficiently. Finally, we'll wrap up with some key takeaways to tie it all together. Let's get started with encapsulation and data abstraction. Encapsulation and data abstraction are like the shields of software design. Encapsulation is all about protecting an object's internal state, keeping it safe from outside meddling while giving us control over how it's accessed or changed. This helps avoid messy dependencies that can haunt us later. Data abstraction takes it a step further by hiding the nitty-gritty implementation details, offering a clean, consistent interface for others to use. Together, they make our code more modular and adaptable. So why bother hiding data in the first place? Well, exposing variables directly is a recipe for trouble. It locks us into a specific implementation. Imagine a point class using X and Y coordinates. If those are public, anyone can mess with them, and switching to polar coordinates later becomes a nightmare. Exposed data means everyone's tied to how you've built things, leaving no room to pivot without breaking everything. Hiding data keeps your options open and your sanity intact. Now, you might think private variables with public getters and setters solve this, but hold up, that's not true encapsulation. Take this point class. Private X and Y with getX, setX, getY, setY methods might seem secure, but it's still exposing the implementation. Anyone using those methods knows you're working with rectangular coordinates, and switching to polar still forces a major overhaul. This is how encapsulation is often taught in intro programming, but it's not enough. Real protection comes from abstraction, not just access control. Here's where data abstraction shines, hiding the details behind a smart interface. Check out this point interface. It's got methods like getX, getY, setCartesian, plus getar, getTheta, and setPolar. You can't tell if it's using rectangular or polar coordinates underneath, and that's the beauty of it. This setup enforces atomic updates, X and Y or R and theta change together, and keeps the implementation a mystery. That mystery is power, letting us tweak the internals without anyone noticing. Let's see abstraction in action with a vehicle example. A concrete interface might have get fuel tank capacity in gallons and get gallons of gasoline. Specific, sure, but it screams I'm using gallons. And limits flexibility. Contrast that with an abstract version. Get % fuel remaining tells you what you need without spilling the beans on how it's stored. The key insight: abstraction isn't just slapping getters and setters on things. It's about expressing data in a way that's free from implementation baggage. Moving on to objects versus data structures, there's a fundamental antisymmetry at play. Objects hide their data and expose behavior, like a square class with a private side and an area method, making it easy to add new shapes. Data structures, on the other hand, expose their data with minimal behavior. Think a square with public top left and side fields, perfect for adding new functions. This split affects flexibility. Objects make extending types simple, while data structures shine when you need new operations. It's all about what you prioritize. Take a procedural approach with data structures. Here's a square with public top left and side, and a circle with center and radius. A geometry class handles behavior, like an area method that checks the shape type and calculates accordingly. It's not fancy, just data and a central function, but it works. The trade-off: adding new functions is a breeze, but new shapes mean tweaking that geometry class every time. So what's good and bad about this procedural style? Adding a new function like perimeter is smooth, shapes stay untouched, and dependent code doesn't care. But toss in a new shape, and you're back rewriting geometry's logic to handle it. The insight here is huge. Don't knock the procedural approach just because it's not object-oriented. It's got its place when operations outnumber types. Flip to the object-oriented side with polymorphism. A square and circle implement a shape interface, each with its own area method. No geometry class needed, each shape knows how to handle itself. Adding a new shape. Piece of cake, just implement shape. Adding a new function like perimeter, though. Now every shape class needs updating. It's the mirror image of the procedural trade-off. This brings us to the fundamental dichotomy between these approaches. Object-oriented polymorphism decentralizes behavior, making new types easy but new functions hard. Procedural centralized logic flips that new functions are simple, new shapes are a pain. Neither's inherently better. It's about what's likely to change in your system. Recognizing this split is key to picking the right tool. The mature take: everything is an object, is a myth. Software design isn't that dogmatic. If you'll add lots of types, go object-oriented. If operations will grow, lean procedural. Complex systems often blend both, objects for one part, data structures for another. It's about matching the approach to the problem, not forcing a one-size-fits-all mindset. Next up, the Law of Demeter, a handy heuristic for keeping code clean. It says a module shouldn't dig into the guts of objects it uses. Stick to talking to friends, not strangers. A method in Class C should only call methods on C itself, objects it creates, arguments it gets, or its own instance variables. It's about staying in your lane and respecting boundaries. Why does the Law of Demeter matter? It cuts down coupling. When objects poke too deep, changes ripple out like a bad rumor. This violation example chains calls from context to options to scratch dire to absolute path. Way too chatty. Refactor it to grab options, then scratch dire, then the path, and you've respected encapsulation. Less coupling means easier maintenance and testing. Code that's less brittle is code you'll love long-term. Finally, data transfer objects, or DTOs, are all about pure data with no behavior. This address class has street and city fields, a constructor, and getters. Nothing fancy, just a data carrier. DTOs are perfect for shuttling info between layers, like to a database, without any logic getting in the way. They're simple, focused, and do one job well. To wrap up, here are the key takeaways from today's deep dive. Encapsulation boosts modularity and flexibility by hiding internals. Objects conceal data and show off behavior, while data structures lay data bare for easy operations. Pick based on your needs. The Law of Demeter keeps interactions respectful, and DTOs handle raw data transfer like champs. Mastering these concepts lets you design software that's robust, adaptable, and a joy to work with. Thanks for watching, and I'll see you in the next one. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.